Okay, today we're going to switch gears a little bit in our momentum unit, and we're going to start talking about collisions. So we've already talked quite a bit about explosions, and we did a lab, so hopefully you did well on that. And now we're going to look at collisions. Collisions are very, very similar to explosions in the way we're going to solve the problem, but it's going to be just a little bit more difficult because we're not going to start with an initial momentum of 0 anymore. So let's take a look and see what we're going to have. We're going to have momentum still being conserved, because we're going to have two objects, and you can always have more than two, but we're going to keep it pretty simple to just two objects. So we're going to have two objects, and instead of them starting at rest and moving apart from each other, what we're usually going to have is one object starts at rest, but the other object has to be moving, because if you have a collision, somebody's got to be moving, right? If you just have two people standing still, they're never going to hit each other if nobody moves, okay? So momentum is still conserved, but the initial momentum of the system is not going to be 0 anymore, because you can't collide if both objects are standing still. So we'll just put that in there. Can't collide if both objects are standing still. We're going to see that there are two different types of collisions, really a couple more than that, but we're going to stick to differences for right now between elastic and inelastic collisions. We're going to start by looking at inelastic. So an inelastic collision means that even though momentum is conserved, kinetic energy is not conserved. Well, if kinetic energy isn't conserved, where does the energy go? Remember way back in our energy unit from first semester, we talked about how energy is always conserved. Total energy always remains the same in a system, but the energy can change back and forth from different types. So what we're going to see is that some of the kinetic energy in an inelastic collision becomes thermal energy. Energy is still conserved, but some of it becomes thermal energy. What we're going to see and what we're going to talk about for right now are perfectly inelastic. And what this means when we have a perfectly inelastic collision is that the two objects collide and move off while stuck together. So the two objects collide and they move off while they're stuck together. So think about this. This is the typical linebacker running back situation, right? They don't bounce off of each other, not if the linebacker's any good. The linebacker grabs onto them and they stick together while still moving. Okay, eventually they come to a stop, but we're just looking for right after the collision. Okay, so we're going to approach this problem very similar to what we've already done with explosions. One hint that I want you to keep in mind as well, and this is kind of a way to check your work, is that kinetic energy is not conserved. Some of it does become thermal energy, so that means that the final kinetic energy is always less than the initial kinetic energy. We're not going to gain any energy. That very rarely happens, and we're not going to look at those situations. So our kinetic energy final is always going to be less than our initial kinetic energy. So let's see how we're going to solve these problems. We'll take a look at an example, and then we have some problems for you to try. So let's say that we have a 20-kilogram medicine ball. That's just a heavy ball that people work out with, if you're not familiar. And we throw it with a velocity of 5 meters per second to a motionless child who's sitting on a skateboard. I don't know why they're doing that, but they are. The child and the skateboard have a combined mass of 60 kilograms, so they have more mass than the medicine ball. We want to calculate the velocity of the child skateboard ball after the child catches the ball. So I always like to draw these, okay? And what I would draw is we start out, we've got the ball, and it's moving to the right, and we know its velocity is 5 meters per second. And then somewhere over here we have a skateboard. So here's my skateboard. You guys know I'm not an artist. So there's my skateboard. And there is the child sitting there getting ready to catch the ball. right? They're just hanging out. They're happy. Okay. And then, bam, they collide. So after the collision, it looks like the child on the skateboard holding the ball. So we're going to kind of divide this into two parts. We're going to look at the before the collision, and we're going to look at after the collision. So let's take a look, and we're going to find the total initial momentum before. So the initial momentum is made up of the momentum of the ball plus the momentum, and we'll just call this the skateboard child. That means the initial momentum is the mass of the ball times the velocity of the ball plus the mass of the child plus skateboard times the velocity of the child plus skateboard. But we know that the velocity of the child skateboard is 0, so we don't have to worry about that. So we only have to find the initial momentum then by multiplying the mass of the ball, which we know is 20 kilograms, times the velocity of the ball, which we know is 5 meters per second. You don't even need your calculator for that because you know that that is 100 kilogram meters per second. So now I know the initial momentum of the entire system. The initial momentum of the entire system, the ball plus the child plus the skateboard, is 100 kilogram meters per second. Well, that means that I also know the final momentum because the momentum is conserved. That means it doesn't change. That means the final momentum also has to be 100 kilogram meters per second. No calculation needed. But I do know that the velocity has changed. So now I have to think about, okay, these guys are all together. They're all stuck together. So the velocity of the ball is the same as the velocity of the person, is the same as the velocity of the skateboard because they're all stuck together, right? If you're holding something, it can't be moving at one speed while you're moving at another speed. So since speed and velocity, we kind of use those interchangeably, we know that these all have the same velocity. So we can say that the final momentum then is equal to the mass of the ball, child, skateboard, times the final velocity. So 100 kilogram meters per second is equal to, well, let's see, the mass of the ball plus the child plus the skateboard is 20 kilograms, because that's just the ball, plus 60 kilograms, because that's the child and the skateboard, and that's times the final velocity of the whole thing all put together. So that means 100 kilogram meters per second is equal to, you don't even need your calculator, you know that's 80 kilograms times the final velocity of everything, because it's all moving at the same speed. So the final velocity, here you might need your calculator. So here we're going to get 100 divided by 80. You could throw that in your calculator. It's 1.25. The kilograms are going to cancel with the kilograms, and we're going to end up with meters per second, which makes sense, right? It makes sense that the ball, once it combined with the person, the ball is going to get slower. The person and the child and the skateboard are going to get faster. So the ball went from 5 to 1.25, and the person/skateboard went from 0 to 1.25, and they roll off together. That's it. That's pretty much how we do these problems. So they're very similar to the explosion. It's just that now instead of setting our initial momentum to 0, we have to find what our initial momentum is, and then everything moves off together with the same velocity. So try those problems, and we will look at the other type of collision, the elastic collision, next class. Thank you.